scientists recreate universe's first ever molecules. Shocking discoveries. Imagine witnessing the universe's very first molecules come into existence right here on Earth, and feeling the ground shift beneath decades of cosmic theory. Researchers have, for the first time, recreated primordial chemistry that prevailed mere hundreds of thousands of years after the Big Bang. And their findings demand a wholesale rethink of how early stars ignited. But here's where it gets controversial. Could long-accepted models of helium's cooling role at cosmic dawn be fundamentally flawed? In a study published July 24th in the journal Astronomy and Astrophysics, scientists report that by imitating the frigid, low-density environment of the young universe, they successfully generated helium hydride ions, EH+, often regarded as the first molecular bond, and traced its collision with hydrogen to form molecular hydrogen, H2. Roughly 13.8 billion years ago, the Big Bang unleashed temperatures so extreme that matter existed only in subatomic particles. Within seconds, the cosmos cooled enough for protons and neutrons to fuse into hydrogen and helium atoms. Hundreds of thousands of years later, electrons attached to these nuclei, allowing atoms to link into simple molecules. According to theory, the initial molecular union paired a helium atom with a hydride ion to create HH+, the cornerstone for H2 formation. Molecular hydrogen then acted as the main coolant, enabling massive gas clouds to shrink and densities to rise until gravity and collisions sparked the first protostars. In stars forming today, fusion kicks off when collisions between atoms and molecules release heat. But this mechanism falters below about 10,000 degrees Celsius. Early universe gas, however, relied on molecules such as HH+ to radiate energy through rotational and vibrational motions, cooling the gas and paving the way for star birth. The abundance and behavior of these ions could thus have dictated the speed and efficiency of star formation in the cosmic dawn. To test this, the researchers cooled HH+ ions to -267 degrees Celsius inside a cryogenic storage ring and triggered controlled collisions with deuterium atoms standing in for hydrogen. By adjusting collision energies, they measured reaction rates across a range of temperatures. Contrary to decades-old predictions, the rate of HH+ destruction remained nearly constant, rather than dropping sharply at lower temperatures. Previous theories predicted a significant decrease in reaction probability at low temperatures, but we saw no such decline in either our experiments or updated theoretical calculations, said Holger Kreckel of the Max Planck Institute for Nuclear Physics in Germany, who co-authored the paper. This insight upends conventional wisdom, suggesting that HH+ reactions played a far more pivotal role in early cosmic chemistry than previously believed. And this is the part most people miss. If helium hydride ions were more reactive under cold conditions, the timeline and mechanics of first star formation and the resulting evolution of galaxies may look very different. Does this challenge a standard narrative of the universe's beginnings? Are our models prepared to incorporate a more dominant role for helium hydride? Let the debate begin. Share your thoughts below. Perry Thaler is an intern at Live Science reporting on space, technology, and the physical sciences, while also exploring renewable energy and climate change. She holds degrees in astronomy and economics from Cornell University, has worked on policy and tech projects at NASA, and studied paleomagnetism at Harvard University, and is pursuing a master's in journalism at New York University. Her writing has appeared on Science Line, Space.com, and EOS.